Yes.
time when I went on for like 2 hours and it wasn't even recording. We good?
Yes.
Awesome. So, I'm back. Did you miss me? No? I don't blame you. A couple of things. Most notably, like the primary sort of thing that I'm sure is at the front of everybody's mind is the impending strike of sessional faculty members, which includes yours truly. I've been fielding a lot of questions about it over email, so I thought I'd, talk a little bit about that, just, so that we're all on the same page, at least the people in this room. So, the strike is happening basically because the university won't give us any kind of percent increase even to match cost of living increases, and their proposal is 1% increase, and as I'm sure all of you are aware, inflation is currently hovering between 8 and 9%, which is if inflation is cost of living increases. Actually, if you adjust the inflation metrics for the same basket of goods that were used in the 1980s, you're looking at more like 15% inflation. But they've modified the basket. But that's how they calculate the consumer price index. Is they take a quote unquote basket of goods, which is supposed to be representative of the goods that a person would buy typically in a month that doesn't include luxury goods and stuff like that. But they've done things like take cigarettes out of the basket, which makes a certain amount of sense because people don't really smoke as much as they used to. But anyway, so the cost of living is definitely going up. The university refuses to pay us any more money than they are currently, and thus a strike forms, a wild strike appears. So the most common question I'm getting about the strike so far is how long is it going to last? And unfortunately, this cannot be known at the outset. The sort of stop condition for the strike, there's one of two stop conditions that may occur. Condition number one is that the union and the employer come to an agreement about what constitutes a fair contract, and that agreement is ratified by the members of the union, thus ending the strike. This path forward requires both sides to agree. Right now they are pretty far apart, so that will probably take time and serious negotiation. The opinion of the union so far is that no serious negotiation has yet occurred. The other possibility for the end of the strike is that a legislative body such as the Ontario government puts forth legislation ending the strike, sending us back to work. Highly unlikely, given that in my understanding the strike is localized to McMaster University. It's not really a province-wide problem, so it's unlikely to have a province-wide solution. So how long is the strike going to last? Generally speaking, whenever there's a strike anywhere, it's usually a pretty safe bet that it'll take at least 2 weeks. That being said, it could end earlier than that if, again, serious negotiations occur. But I'm thinking 2 to 3 weeks is probably how long the strike is going to last. But again, this is supposition on my part. I can't be sure about that. Nothing is for certain at the moment. However, from a scheduling perspective, if this strike takes more than 2 to 3 weeks, we start running into issues of how the heck are we going to finish this class before September starts. And this is, I think, like, basically, if the strike's not over in time for this course to be completed, then it's going to run into September. And it's going to start affecting the main body of the courses that are being offered at the university. So, in general, the response to strike action by either TAs or sessional, part-time instructors is normally the suspension of all classes at the university, regardless as to who's teaching them. That's normally how these institutions respond to labor action of this type. A TA strike will shut down classes. A sessional class will sessionals can also shut down the classes in their entirety. You'd be surprised how many, it's a pretty high ratio in some departments of sessionals that teach the courses. In CAS, it's reasonably low, but in some places it's actually, I couldn't give you an exact percentage, but I wouldn't be surprised if it was north of 30% of classes. So that's what I expect the response of the employer will be, is that classes will be put on hold until the strike is completed. I don't know how or when we are going to finish this class, but I am under contract to deliver this class, regardless as to whether that contract has been interrupted. So, at some point, everyone will receive their credit for this course, if you're, passing the course at least. We'll break through, we'll make do, we'll have to make some concessions in terms of course delivery, but in the end, this is not the end of this class. Your efforts so far this semester have not been wasted. Certainly, if you consider the material that you've been learning to be valuable, your efforts have not been wasted, regardless as to whether you're obtaining the credit or not, but yeah, so for those of you who may not have seen the announcement, the date that has been set for the beginning of the strike is this Friday. So classes this week will continue as scheduled and will continue as normal until such time as the strike starts. So that means that your labs this week will continue as scheduled and as normal. Assignment 1 is due in like an hour or so. Assignment 2, it seems you'll have a reasonably long time to work on it. So I expect everybody to get 100% on it. Don't let procrastination, procrastination is not a great policy at the best of times. It's especially not a great policy when you're not sure when the thing is going to be due, because the assignment is going to be due basically quite quickly after the classes resume. You'll have some time, but not as much as you had over the break. So it is my strong recommendation that once the strike starts happening, you get to work on the assignment. With respect to communication between myself and you guys while the strike is ongoing, in theory, I'm not allowed to be your instructor while the strike is ongoing. That being said, the TAs are not going on strike, so you're welcome to talk to them about questions you may have with the assignment material, etc. I'm probably going to answer emails anyways, you know, even though that technically makes me a scab, but, you know. It's a difficult situation, and I understand that sort of outside of the contract that I have formed with the university to deliver this course, I also have a duty of care to my students, regardless as to whether, you know, what the status is of my work situation. So I will be exercising that duty of care to the extent that I'm able during the strike, but classes themselves will be suspended while the strike is ongoing. Are there any questions before we, yeah?
By the time the strike starts, how much of the content would we have covered for assignment 2?
Well, excellent question.
Will we still have access to the stuff on Avenue?
Probably.
You can just read the lectures.
I don't think they'd lock you guys out. They might lock me out.
Well, I'm just wondering, maybe I could just download everything.
Yeah. So if you do get into I'll answer your question, and if you do get into a situation, any of you, where the course material becomes unavailable to you for any reason, get in contact with one of the TAs. We keep, oddly enough, we keep all of the course material in a Git repository that is not on the university servers, and our primary means of communication between the TAs and myself is also not administered by the university, i.e. we use Slack. So even if the university were to lock me out of my email, which is a possibility, although not exactly a possibility, as I'm still a registered PhD student, and I'm pretty sure that I still have my email on that basis, but if I weren't, they could very well lock me out of my email. There's still the Discord, right, where we can communicate with each other, although I know I'm not terribly active on the Discord, but you know, that's why I have TAs. So basically, there's nothing critical that's on the university's infrastructure except for the master gradebook. And that doesn't really matter until, you know, that can wait till we get back. And if you're really curious about, you know, what you got on a particular thing, then the TAs would be happy to help you with that. But yeah, no, none of our, we don't keep any of our critical infrastructure on university servers. So in theory, all of that will be available upon request, certainly, if, but I don't expect them to shut down Avenue. That would be, like, again, it would be targeted at me, not at the students, if that makes sense. So, assignment 2 coverage. Let's take a look. So, so on Wednesday we're going to be talking about strings and string formatting, which is like, we're going to be going through the string library. We're going to be talking about how to format strings and a lot, and we'll be covering file I/O, all of which are topics you need for assignment 2. We'll be covering this Wednesday. It's basically more pointers. It's like in order to work with strings in C, you have to already know how to use pointers, which is why this comes after pointers and not before. So all of that will be necessary. The other thing that will be necessary, sorry, purple, this is the purple class. Eggplant. The other one, you will need data structures as well. So, the material in here is not so difficult to grasp that you couldn't pick it up yourself with self-study. Particularly, if you hunt through my archives on the YouTube channel, you'll be able to find me covering this material in both, you know, this class, 1XC3, and other class I teach on C programming as well. This material is covered a couple of times on the YouTube channel, so I will be covering it when we get back, but if you'd like to work ahead on the assignment while the strike is going on, I'm not going to shut down those resources while the strike is going on, even though technically, probably according to the union, I should be. It would just be a pain in the ass. Can you imagine? Like, I've got like 600 videos going through each one of them and disabling them.
Private.
Yeah.
Just private all of them.
Yeah, one at a time. Come on, man. Yeah, no, I'll just conveniently forget and leave it up.
Oops.
Yeah. So yeah. So you should be able to get through the first half of the assignment on the stuff we're going to cover Wednesday. The second half of the assignment will relate to this stuff, but you know. Ooh, I should give you a warning about assignment 2. Actually, there's one question on there which is really tough. So, yeah, I know, right?
Of course.
I just want you to be aware of this going in. This question here, simple expression parsing. This is a toughie. This is like a 4-star problem. Basically, you should view this problem as most of the problems that I've given you so far have been so simple that like the underlying structures which perform computation are implicit in the structure of the problem. In this case, it's less so. You kind of have to decide what some of the internal mechanisms look like yourself. This is like, well, first of all, very good practice for solving real problems. This is as close as we're going to get in this class to like the type of programming problem that you would be expected to do in industry, right? This is like a real problem, right? And it's sufficiently difficult that like absolutely every single person in this room is going to come up with a different approach to this problem. And I feel that it's really like valuable for you guys to see a problem, at least one problem like this in the course of a course, right? So, you know, in 1MD3 terms, this is like close to the checkers problem. But yeah, so just be aware of that problem. Again, if you're having an undue amount of difficulty with it, please talk to the TAs. They'll be able to give you some hints. But yeah, so, right, we should probably talk about our actual lecture topic for today. Are there any other questions about the strike? Yes?
Is it possible that at the 11th hour they changed their mind? Like, should we just assume that it's not happening until it is happening?
I think it's a good mental attitude to assume it's not happening until it happens, right? If that, like, you know what I'm saying though, right? It's like, you should still, like, be working hard on the course up until the point that the strike is called. However, like, what's the percentage possibility that the Large Hadron Collider creates a black hole that engulfs and destroys the Earth?
At least 1 in 5.
Yeah, lower than that. So
I don't know. I also have a question. If you're technically not our professor while the strike happens, can you help me with assignment 2?
well, it's not even that I'm not your professor. It's that I'm not allowed to perform instruction on like it's not that
When
I'm
you do
just
it for
like
me, you're not instructing me.
No, I'm not a civilian. I'm not a civilian while the strike goes on, right? I'm still the prof. I'm just not allowed to perform in profly duties. But I mean, talk to the TAs because they're like really like good at everything, so they'll be able to help you. Okay. Any other questions? I realize that the strike is not ideal circumstances, but as with most things, like, you know, life is not an ideal circumstance. If you wait for conditions to be ideal before you embark on your great journey, then you will never embark on your great journey, and you will stay in your parents' basement for the rest of your life.
I was
So,
already planning on that. I was already planning on that.
yes,
What about our final exam?
yes.
When it's going to happen? Like,
I don't know. The last week of classes. Whenever the hell that's going to be. I will try, after the strike is finished, to pick up where we left off as, like, you know, we'll try to pick up with as little interruption as possible. Like, my design goal will be for it to be almost like the strike never happened. That's my goal, but, like, given what scheduling may come, it's not, you know. We'll see, it depends. If it lasts 1 week, that's much more convenient because we can just move the whole schedule down by 1 week. But if things start running into September, like, I have no idea what, like, I don't know, maybe we could, like, compress 2 weeks into 1 week, but that was like it's already running at, like, you know, double time. That would be like compressing a whole month into a week. It's like, this is a summer course, god damn it, and that's the worst possible time to have a strike, but, you know, it is what it is, I suppose. Yeah. Anyway, so let's talk about makefiles. So, makefiles are a way of organizing the manner in which you compile programs, essentially. Makefiles are actually a very usefully generalizable way of doing things. The whole point of a makefile is to take all of these complicated commands that you guys have been using to compile C programs and other things in the command line and provide some structure to it so that only those invocations which are necessary actually get run. Make is another program that reads the makefile and performs the actions encoded in the makefile where appropriate. It's a little more intelligent than just simply entering your compilation command into the command line. So, but in order to understand makefiles, we must briefly review the stages of compilation. Most particularly because we are going to break the chain of compilation at a particular point so that we can use makefiles more effectively. We're going to be working with files that are direct in object code. Oh, by the way, .h files are also C source files. Just throwing it out there. I understand the TAs were like having to have arguments with people that, like, some people thought .h files weren't C files because they didn't have the .c extension. Sadly, no. Sadly, no. So, recall the stages of compilation. At the preprocessor stage, we process the preprocessor directives like include and define statements. We prepare the file for parsing. The compiler itself parses and generates the abstract syntax tree. That abstract syntax tree is then assembled into machine or object code. Object code is going to be important in this, in what we're about to learn. After assembly, you link with other object files if applicable. So, in general, the problem that we have with compilation in general is that it takes a long time. You guys probably have not had to worry too much about compile times with your projects or your assignments and stuff you've done in lab so far. But if you're working on any code of any reasonable medium or large size, in particular, if you're working with higher levels of optimization, because using the optimization flags will vastly increase the amount of time it takes to compile anything, although you do gain benefits from that on the other end. What we want to do is we want to be able to perform a staged or modular compilation. So we want to be able to compile individual C source files separately from each other, and then, at the linking phase, bring all of our compiled object code together into one executable. So, how this looks, sort of from a mechanical standpoint, you will have several C source code files. Each one of those is compiled to object code separately using a separate invocation of the C compiler. So I've got file 1, 2, 3, and 4. I compile, say, 1.c, 2.c, 3.c, 4.c. We compile these using a special compiler invocation to 1.0, 2.0, 3.0, and 4.0. We compile them to object code. Then finally, we have one more invocation of the compiler, which takes all of the object code files and compiles them into one executable. Basically, the final invocation only performs linking on all of the precompiled binaries. So what's the advantage of this? Only that which is modified needs to be recompiled to an object code file. So let's say you're working on this project, and your most recent changes to this project are only in 2.c. You can recompile 2.c, create a new 2.0 file, and link that file with the existing 1, 3, and 4.0 files. They don't need to be recompiled. In this way, you are only compiling that which you are modifying and saving a whole bunch of time. Does that make sense? Of course, the problem with all of this is that sounds like a huge pain in the ass, right? Keeping track of timestamps, right? Wouldn't it be so great if we had a program that did that for us? That program is make, and now we're going to learn how to use make in today's class. But first, let's just talk a little bit more about object files. So, what is the point of an object file? Object files are machine code that is compiled from source code without the code for any called functions or any other source code files. So, in the object code, if, for example, you're using printf or scanf or any of the string library functions or anything like that, the definitions of those functions do not appear in the object code file itself. Those definitions are provided at the stage of linking, right? The final stage of compilation. Instead, object files contain links to the needed functions in the needed files and libraries. So you can kind of think of it like the way that web pages work, right? You may not know this, but when a website contains an image, what it's actually doing is it's a website that contains a link to an image file that is contained in the same directory on the same server, right? Possibly you can link to image files that aren't on your own local server, but then you don't own them, so if somebody deletes it, you have a broken image inside your web page, right? So that link is right there in the web page, like the HTML file. The image itself doesn't get brought in until that web page is rendered, right? So we're talking a similar idea here. So, object files are binary encoded, not character encoded. So there's no point trying to look at them with cat or less or any other file viewer program, unless it's a hex editor, but there's really no reason to want to edit executable files since they're encoded in machine instructions, and any modifications you make to it, are basically gonna screw up, some register right in some line of code, and you're just going to introduce bugs. There's no way to intelligently modify files after they've been compiled. I hope all of us can agree on that point at least. So, by compiling an object file for each source code file separately, the object file only needs to be updated if the source code is updated. This can produce massive speed boosts in compilation time. It is not an exaggeration to say that some projects take hours and sometimes days to compile. Particularly with optimization. So, this is how you perform object code compilation. So, using object files correctly requires effort. We can compile batches of source code files to object files using glob patterns and the -c flag. So, a regular invocation of GCC will result in an executable file. Using the -c flag changes the mode on GCC to produce object code files instead of executables, right? So this is how you get your .o files. So the problem then, however, when we go to compile our program from the created object code, essentially what we get, we have to list all of the object code file names in our invocation of GCC, which we are trying to produce the executable from, right? This is just long and bothersome, right? We have to manually include our object files, which is tedious and time-consuming. So, we're saving compilation time, but losing time to longer commands. Typey, typey, type. We want to do as little typing as possible. Question?
Why can't you just do start out?
It's possible with this invocation that you produce a main.o file, right? And including main.c and main.o is probably not a good idea. And you would have two definitions for main, which is, problematic. You might be able to get away with using glob patterns to, you could say, live star.o and etc.o. Like you can compress this using glob patterns, absolutely. But using makefiles, we can get it with even less typing than this. Spoiler. Okay, spoiler warning. Once you have a makefile properly set up, all you have to do to compile everything you need compiled is type make, M-A-K-E, and then there you go. It'll do everything for you. But you have to know how to properly configure the makefile. So, make is a program which automates the compilation process. Make compiles only those source code files that need to be recompiled to produce the executable. It does this by checking the time at which your source code files were last saved and the time when the program was last compiled. So basically, all of your object code files will have a timestamp, right? The time at which the object code was created. If the C source code timestamp is more recent than the object code timestamp, then the source code has been modified since the last time the object code was produced. This is the indication that make uses that the file needs to be recompiled. Right? Does that make sense? So, make requires a special configuration file called a makefile, which tells it which files to compile, which compiler to use, etc. Makefiles are not bash scripts. This is a different thing. While makefiles can and often do contain bash commands, a makefile is not a bash script. Makefiles can call bash scripts, they can invoke bash scripts, but you can't, for example, use a bash if statement inside of a makefile. So, makefiles are composed of rules. This is what a rule looks like inside of a makefile. So basically, we'll do an example of this, but what a makefile is it's a bunch of, optionally some variable definitions at the top, and then a bunch of these guys, right? So, we have target, prerequisites, and recipe. The target can be one of three things. You can have an executable file, so like your main executable that you're producing at the end of everything. You can have an object code file, .o file, and you can have a so-called foamy target, which functions as a special command. For example, a common one is clean. Another one is all. You can set a makefile up so that if you type make all, you can compile you compile all of the possible executable files if you have multiple executable files in the same directory. We'll get into how to set up foamy targets. A prerequisites, this guy right here, prerequisites, are all the files that are used as input to create the target. So if you require, if you have a C program that sort of has a hierarchical structure with more than one level, the middle bits might depend on some bits in the lowest level, and then the level above might depend on just things in the mid-level. The, whatever files are necessary in order to compile the object code that or executable that you have specified by the target, basically any files referenced inside of the recipe should go in the prerequisites. A recipe is a bash command that make executes in order to create the target. So what you should put right here is either the GCC invocation or whatever compiler invocation you're working with here, or in the case of something like a cleanup routine, any of the bash commands that perform the cleanup that you want to perform. And we're going to talk about how that works. So, each recipe line must be started with a tab character. Spaces are invalid syntax. So, one tab right here, nothing else. If it's spaces, then it won't compile. So, here is a simple example. Recall the files that were used in Lab 6 to create static and dynamic libraries. We had top.c, sums, products, and sea shanties. We used lots of fancy compilation methods to create static and dynamic libraries, but you can also compile these using more simple invocations of GCC, such as this guy right here. This is assuming that sums, products, and sea shanties have all been compiled to object code files prior to compilation. Make sense? Good. If we write rules to produce all of the object files and the final executable into a makefile, we would get the following. So, to produce top as an executable, we require top.c, sums.o, products.o, and sea shanties.o. This line here is the GCC invocation from the previous slide. That compiles top, right? Sea shanties.o requires sea shanties.c, right? Compilation line to compile sea shanties.o from sea shanties.c. Similarly for products and sums. So this is how a makefile works. When you type make with no rule specified, it will assume that you want to make the whatever the first rule is in the makefile. So it defaults to the first one. In this case, top. That's why when you're writing makefiles, always put your final executable at the top. It should be the first rule. Okay? So I've been doing this whole thing without microphone. My goodness. Can I get the microphone? Boy, I spent 1 week away. I forget all of my tricks. Test. There we go. Now I don't have to shout quite as much. So, I probably will anyway, though. Where was I? Yes. So this is what make does. It examines, so when it runs a rule, the first thing that it does is it examines each of the prerequisites. If there is no rule corresponding to the file, it skips it. If there is a rule in the makefile corresponding to that prerequisite, it will pause this guy and execute this rule first. Right? A rule will only execute if whatever the prerequisite is has a more recent timestamp than the file specified as target. So if sums.c has not been modified, this rule will not execute the recipe. So it'll jump back to the top and examine products.o. Jumps here, performs the timestamp comparison, right? Then jumps back up again, right? And that's the procedure by which it checks to see what needs to be compiled and then compiles it. Does that make sense? Good. Right. So, and just before we, let's finish this section and then we'll do an example. So, now that we have our makefile in place, we can start compiling. To compile the quote-unquote default goal, simply type make. To compile any of the targets in the file, just specify the target. So make sums.o or make top. To invoke a foamy target, just type the name of that foamy target. Nothing could be more simple. Once the make file is set up, all you have to do is type make, and then the thing that you want to compile, and it does so. So, how does it work? On default invocation, i.e. just calling make with no arguments, make will use the first rule as its compilation target. Therefore, your top file should be at the top. Whether the target is default or specified, make recursively processes the rules for all prerequisites of the target rule. Recursively just means that it recursively steps down the prerequisites tree and looks down the tree and processes and pulls back up and goes back down until it's got everything together, and then it processes the final file. If the source code file is newer than its corresponding object file, or if you want to make it a little more general, if the prerequisite is newer than the target, it executes the recipe. For testing purposes, the touch command updates the timestamp on a file without modifying its contents. Any object file which needs to be linked to other object files will be regenerated as well if any object file it needs is newer than itself. So, for example, let's say sums.o has been modified but top.c has not been. Both sums.o will be reproduced and the executable for top will be reproduced, because top will then have a prerequisite that is newer than its target, because it will have just been produced by the compilation. Yes?
So is top.c the source file? What's the
Yeah.
difference? Yeah, I guess I'm confused, like the difference between source file and object file.
Right. So C source code files are .c,
Right.
right? These are the files that we modify in our text editor when we program, right?
Mm-hmm.
The object files are produced by compilation as an intermediate step.
Right.
We're breaking the compilation up so that we compile each one of these files individually before we compile them all together.
Okay.
The object code files are the products of the individual compilation of each of these files. Make sense? Any other questions at the moment? Okay. So. Yes. So, example time. So we have top.c, right? We have sums.c, we have products.c, and we have C shanties.c, right? All C source code files. I'm going to make a new make file, so I'm going to rename this one. Now, see how it changed the icon from a hammer to just a regular file icon? A very, very important thing to note: the way that the make program finds your make file is by the fact that it is named makefile. Make will attempt to find a make file in your current working directory. If you don't have one, then it doesn't find it, and basically make fails, saying that you have no make file. So you can't just, this is one of these cases where you can't just pick an arbitrary name for the make file. The make file's file name must be makefile. Otherwise it won't work. Make sense? Question?
Is there no file extension?
No file extension.
So just write make file.
Just write makefile, yeah. Yeah. Again, file extensions are, they exist, but they kind of don't exist. So, this is good. So, target number 1, top. Nano will be nice to you again and probably warn you if you're using spaces instead of tabs. So top requires top.c, it requires sums.o, it requires products.o, it requires c shanties.o. The recipe, GCC, w all, output top.c, sums.o, products.o, c shanties.o. Simple. Sums.o is our next target, requires sums.c, GCC, w all, with C flag, sums.c. That seems like it's slightly different from this guy. You want to specify an output file name. Output file name sums.o. There we go. We have basically same thing, products.o requires products.c, GCC, w all, co, products.o, products.c. And finally, c shanties.o requires c shanties.c, GCC, w all, co, c shanties.o, c shanties.c. Save. There we go. So, let me just remove top. And there we go. So, if I type make, it tells you what commands it performs in which order it performs them in. So, it started with sums, then products, then C shanties, then all of them. And if you'll notice, if I just bring up the make file, that just happens to be the order in which the prerequisites are stated inside of the recipe. My goodness, what a coincidence. It's not a coincidence. That's how it does it. Yes?
In the make file, you said not two spaces, or do you mean just for like the GCC?
Oh, just any recipe line must have a tab instead of 8 spaces. You're allowed to use spaces like inside the commands and stuff. It's just it'll be a syntax error if you use spaces there. It's like there's kind of like a controversy in computing and among programmers as to whether spaces or tabs are correct, and this is sometimes enforced at the level of the compilers and programs themselves, and this is one of those cases where it actually cares whether you use tabs or spaces. It can just be frustrating to have put spaces there and not know why it's preventing you from doing anything. Any other questions? All right. So, you'll notice inside of the directory we have all of these object code files sitting around cluttering things up. I'd like to show you one or two little extensions that you can do here, just for fun. So let's say we wanted to take all of these object code files and put them, like sort of tuck them away inside of a subdirectory so that we don't have to look at them, right? Let's say that, in order to perform any of these, we require a thing called objects to exist. So, objects has no prerequisites, and make dear objects I'm going to do this and get it because it's faster. So, let's say we require all of these guys to be in there. Hopefully this works. You never can tell. There we go. We have an objects folder which has been created. If we navigate into it, you'll see we have our .o files inside of it. And we can, in fact, remove star.o, and everything just works. The .o files are no longer being dumped into the main directory. Make sense? So the thing that I'm trying to impress upon you guys there is that these file names, which are being used inside of Makefile, are not just file names. You can have directories. You can use relative or absolute directory addressing anywhere you're using a file name. So, if you're trying to pick things out of subfolders, you specify the folder. If you're trying to put things into subfolders, you specify the folder. If you're trying to go up a directory, what do you use? What two characters? Yeah?
2 periods.
2 periods, yes. So, good. Wonderful. So, let's continue on then, shall we? Well, I think I'm going to show you guys Foamy Targets now, just for a moment. So, Foamy Targets. A foamy target is a target that is never actually created, but otherwise specifies a series of dash commands which you may want to work into the execution of any particular thing you're building. So, for example, cleanup has no prerequisites. rm star.o in objects. So, or even just remove recursively objects. Now, when you clean up the object code files, when you want to compile again, you'll have to reproduce all of them. So this kind of, to clean up, negates the purpose of speeding up compilation because you're deleting that which is speeding up the compilation. However, you know, if you're doing a release version or you're putting up a nice version on GitHub or in your master branch or something like that, then, you know, cleanup routine is like a commonly included thing. Another one that's commonly included is all, or like a complete rule. So sometimes you have a rule that doesn't even have a recipe. Its only purpose is to call other rules. So in this case, it might call top and then it might call cleanup. So the way that one invokes these, make all. So you can see it executes this command because it first executes top and then it goes down and executes cleanup, right? Top, then cleanup. Make sense? It's very, very versatile, right? Now, again, the recipe lines are not bash script lines, right? So if you want something fancy like looping or if statements, you write a separate shell script file and then invoke that from your make file. Yes?
Why did it run GCC commands if the source code wasn't modified from the last command?
That's a good question. Oh, probably because objects didn't exist. I probably messed that up. Like objects, because it was just recently created, will be newer than the target, so that activates the creation of the target, despite the fact that the folder doesn't need to exist. So that would be one reason to not. Like, here's a question: if I run it twice, will it do that again? Make. So it didn't make objects, but it keeps making these guys. Interesting. Did I mess it up somehow? Let's see what I got in the slides. I don't know, I have to move on. There's some problem with it somewhere. But, well, maybe I should try to fix it. Alright, let's see here. What happens if we delete this? Ah, there we go. That was the problem. So, top is up to date. Nothing more needs to be done. However, if, for example, I touch, sums.c, then it compiles only this guy and that guy. So, there we go. I did have time to fix it, in theory. I won't know if I didn't have time until the end of class. Question?
So when you make the directory objects, we don't need to put it at the end.
You can just have it there, right? Directory creation and deletion is like possible, but has like certain limitations as demonstrated here. What you could do is you could just leave it and assume that have it assume that the directory is there, and if the directory isn't there, it'll throw an error, right? But yeah, it's because I was trying to do something fancy and create it if it didn't exist,
Oh, okay.
right? And that was messing things up here. But yeah, if you don't like work directory creation and destruction into the script itself, you can just leave a directory there and assume it's there. There you
And
go.
we'll put them in the directory.
Yeah, it's still putting them in the directory.
Okay.
Yeah. Question?
So if you run like make cleanup right now and then make, it'll give an error?
It should. Let's take a look. Make cleanup. Yep. Make. Yep. Assembler messages. Fatal error. Can't create objects sum.o. No such file or directory. There you go. Any other questions? Cool. So that's roughly speaking foamy targets. I'm pretty sure that foamy targets are a thing that we're gonna talk about, but at any rate. So, variables. I finished my work while you were still complaining about it, and programming is hard. Programming is not as hard as if you know how to use it. It's one of these things where, like, it becomes very easy if you learn a little bit about how it works. So, variables. As with so many things, we can make things once again simpler in the long term by making them more complicated in the short term. Makefiles support variables, roughly speaking, similar to how you would do them in shell scripting. Variables, once again, need the variable substitution operator to work. This time, enclosing the variable name in round braces is considered good etiquette. You also don't have to worry about leaving some white space around them this time, but don't go overboard. When set up correctly, variables let you control many things about our compilation process from a few lines of code at the top. So, for example, we might want to specify what the compiler is. Let's say we wanted to make this, let's just say that you're, you might want to switch between GCC and Clang to see how the two of them compile the same files differently, right? Or maybe you like some of the optimizations on Clang a bit better. CC is GCC, or Clang, or whatever you want, right? You don't have to be quite so strict about spaces. And then, substitute the CC variable anywhere you are using GCC. Incidentally, CC is also a command, and it defaults to GCC. It's like whatever your C compiler is. It's one of those funny little Linux things. But another thing you can include is flags. So let's say W all and O. Flags. So, for example, how would you want to turn on O3 optimizations, for example? And let's imagine that you've got more than 4 C source code files that you're compiling here. Let's imagine that you're compiling more like 400, right? by setting a flag variable and having those flags applied to each invocation of GCC, you sort of have global flags, right? If you want to turn on O3 optimization, all you have to do is put it at the top, and then it will automatically apply to everything, right? Which, of course, is, we're all about that. Oh, the one thing you have to be careful of, though, is that if your last one expects an argument, then you have to not interfere with that. So you have to put stuff before. But, yeah. There you go. And I know it's like, these are so simple that it didn't really show up, but like O3 optimization did take slightly longer. I think it was perceptible to humans versus, regular optimization. We could time it, but who cares? But yeah, so variables, yeah? Things that you would want to repeat. You could set what the object's directory is at the top and carry that through in the form of a variable. This allows you to be flexible with it at a later point, right? Good. So, abstract out the compiler. Abstract out the compiler flags. Abstract out the list of objects. You don't even have to include, like this is a lot of repeated writing, right? So you can abstract out the list of objects that you want to do as well. There you go. So, and here's where we're talking about foamy targets. Although it isn't required, it is conventional to include a cleanup foamy target, which deletes files used during executable generation, but which are not needed afterwards. Specifying no prerequisites makes this a standalone rule that does not depend on any other rules being executed. And of course, rm-f, the F flag means force. So basically all that does is it stops RM complaining about trying to remove files that don't exist. Which normally I think is an error, but Oh, that's another thing to note. If any of the commands which make is executing results in an error, it will terminate its process immediately. So if something fails to compile because of a syntax error, for example, make will immediately fail and just display whatever GCC said was a syntax error. Make sense? I would like to now just show you, I think I showed you this already, but maybe I didn't. So my thesis, right? My thesis is written in a document generation system called Latex, which if any of you have any idea, yeah, I see some nodding heads, yeah. If any of you have any ideas about wanting to become an academic inside of this discipline, I think Latex is pretty common in science, like straight sciences as well, yeah? Yeah, LaTeX is superior to all other document generation systems because all of the LaTeX source files are stored in regular plain text and not like horrible Microsoft pseudo XML terribleness. It is highly extensible. LaTeX documents have just this general quality of looking good without much effort a lot of the time. All of my lecture slides are produced in Beamer, which is a package for LaTeX. So all of my slides are done in LaTeX. My thesis was done in LaTeX. Anyway, the thing that you do with LaTeX documents is you compile them, just like you compile everything else, and at least if you're on Linux. So I wrote a makefile for my thesis, So this is kind of like an example of, yeah, there we go. This is an example of a make file in the wild, so to speak. The thing about LaTeX is it does require some finagling when it comes to compilation, and it does create a lot of like miscellaneous log files that are not very useful. Has anybody ever actually used LaTeX in this room? Yeah, you guys will notice all of the friggin' like .out, .toc, .acr. Like, what is all this nonsense, right? Like basically, a lot of the big add-on packages that you might use with LaTeX create their own like intermediate files, which it then just dumps in your folder. Because basically LaTeX is assuming you know how to use makefiles, and you know how to set things up to automatically create things. But anyway, so with this, so first of all, makefiles are useful for things other than just C programming, right? Literally anything where files are created and destroyed and compiled, you can use a makefile for. Now there are more modern methods, but basically all of the modern takes on how to perform the same functions use this as their ancestor. So understanding how makefiles work will allow you to understand how most programs of this nature work. So anyway, I have a phony target in all, so that's build and then clean. Build runs through several compilation processes. It turns out with LaTeX, you have to compile it once, then you have to compile the bibliography, then you have to compile it to integrate the bibliography, and then you have to compile it one more time to let all of the like section names pop in and like to generate the table of contents. So that like you can imagine like typing that every time, right? It would be terrible. Show just uses, I show my PDF with my particular PDF reader, and then clean like just finds every every file with any of the particular garbage file extensions that LaTeX generates, and it just removes all of them. In addition to recursively looking for backup files with particular patterns. We're going to learn how to use find after the strike. We have a unit on that. So find allows you to find files. Not surprisingly. Oh, one other thing. Doesn't matter if makefile is capitalized or not, so long as it's named makefile. Sehr gut, yeah? Yeah. So, another phony target which is typically included is all. This isn't necessary unless a makefile has multiple executables that it can't produce. But making all, writing a phony target that just makes all targets is, a useful thing to put in a makefile. So, yes, if there was more than one top file, for example, that could have gone in the top slot. The all rule typically doesn't do anything by itself. It just queues up all valid final targets for generation by making them prerequisites. So we've seen this a couple of times. Ooh, one other thing I just wanted to point out about my makefile here, which so this whole process takes like a minute and a half. So I also have a quick phony target, which is sufficient to generate like positions of figures and tables and stuff, so that you can do a quick check to see if your table is correctly constructed, and then continue. You can compile the rest if you want to. It just saves time. And especially like if it's the type of thing where it's like do a little edit, see what it looks like, do a little edit, see what it looks like. Yeah. Anyway, so good. Any questions about makefiles before we move on to testing? That's is it like it's kind of like simple in theory, but you know, implementation takes practice, I think. Yeah. Personally, I find makefiles a lot easier to work with than Bash, like Bash scripting. But you know, your mileage may vary. So, let's talk about testing, automated testing. So, automating things is both efficient and satisfying. So, let's automate one of our more tedious programming tasks, testing. When testing a program, we compare the expected output of our program to the actual output. Of course, this only works if the outputs were produced from the same input. You know, in theory, the whole operational assumption of computing is that if you provide the same input twice, you'll get the same output twice, right? So, the expected output can be generated by a number of processes. You can either have it as a design, like you design what the output should look like and then expect your program to behave in that manner. You can have your output produced by a different and perhaps less efficient algorithm. So this actually happens more often than you might think. There's sort of a more brute force, less efficient way of performing something that works but is slow, and your task is to create an improved, optimized version of that algorithm. It is appropriate in that instance for you to use the old algorithm to generate test data for the new one, because they're supposed to do the same thing. So you know when your more efficient algorithm is performing correctly, because it's still doing what the old one did, and then maybe you can benchmark it to see how big the improvement has been, right? And under what circumstances you get improvement. So, another source of output might be customer requirements, although you are in a very fortunate position if your customer requirements are sufficiently specific that you can actually generate test data from them. Generally speaking, customers are terrible, they have no idea what they want, and when they do know what they want, they do not phrase it sufficiently mathematically for you to be able to usefully use it in the program most of the time. There's a whole field of engineering called requirements engineering that's whole purpose is to take what we call natural language requirements, that is to say requirements in spoken speech or written, language, like, the types of languages that humans use, and translate that into formally mathematical specifications that may be used to, generate test cases. So the question might become, how is it that we go about testing to see if there are differences between two different files? Program output can be captured as a file. If we capture program output as a file, we can compare that file to another file that contains the correct answer. So, the way that we compare two files to see what the differences are between them is a very simple program called diff. So, diff file 1, file 2, file 1 being this, file 1 being that. If you, it's a sufficiently short file that you could probably spot the difference yourself, right? It's right there. But we also have a program that will spot the difference for us as well. And because this is Linux, you can take the output of this file, test it to see if it's 0 or not, like test to see if it returned any lines of code. And if it returned lines of code, you can do something else with a script, do an if branch based on the size of the output of diff that will, tell the user, oh, you messed up here, there's a mismatch, etc., etc. Because diff will not do much if the two files are the same. Make sense? Diff is a very useful program. So, up to now, we have been comparing our expected and actual outputs manually. This is slow, tedious, and a bad use of human resources. The diff command automatically reports the differences between two files. Combined with the output capture character, this guy, greater than or closing angle brace, we can run a program, collect its output, and compare it to a previous file that gives us our expected output. So, if we execute foo, we can capture the results that foo produces, pardon me. We capture the whatever foo puts out to standard output, and we save it to a separate file. That's what this character does. Naturally, we can integrate this sequence of commands into both bash scripts and make files. So, we've not actually run top yet, right? So, it takes a while. In fact, let's just modify top for the moment to remove the sea shanty, much as it breaks my heart. There we go. So, we run top, right? This is the produced output. If we redirect top to top.out, for example, nothing is produced inside of the terminal. This terminal output has been captured, so it does not display inside of the terminal itself. However, top.out has been created, and if we take a look at the contents, there we go. Right? So, we can take that file and we can say this is our good version. Top good. Move top dot out to top good out. Good, excellent. And then let's modify sums just to introduce an error. Introduce an error. There we go. Recompile. There we go. Now we run this again, capturing the output. There we go. If top.out and top good.out. And you can see diff reports that in top 2 plus 2 is equal to 5, which is wrong. And in top good, 2 plus 2 is equal to 4, which is correct. Does that make sense? It's pretty cool, right? Automated testing? Yeah. So, this is a procedure that we can actually integrate right into our makefile itself. So, add another foamy target, test. We'll include that in all. So test is going to require top.c, or just top. Shouldn't be a problem. So we run top.c, or not dot C, pardon me. We run top, we capture it and place it in top dot out, and we diff that with top good dot out. Right? So now